So there will be just a moment. Thank you. There will be 4 of us. Your sister. Shina, Henley, and Steph. Oh, and Izzy, and Stephanie. Okay, so we're recording. I always like to start off the session with, what questions do you have?
No questions so far.
Okay, no one has any questions?
No questions.
Okay, then what I'm going to do is I'm going to be doing some problems from the chapter problems and show you how I would address them and how I would tackle them. And we're going to go from there, okay? And if you have any questions, you need to pause me somehow or other, get my attention, probably verbally, and ask a question. Is that clear?
Got it.
Got it.
Since you all have your videos turned off, I don't know what you're doing, but here, I'll tell you what. If you want to turn your videos off, I can open my participant list and we'll work it this way. When I ask a question, if you've got it, you give me the thumbs up. So you can find that by opening up your participant list. And at the bottom of the participant list, you can go to reactions or whatnot, and you can give a thumbs up, means you got it. Thumbs down means you don't got it. Okay, so let me change my share screen to the Elmo. So what you should be seeing now is a piece of paper with problems written on it. So let's go ahead and get started here. This is on page 21 and page 22 from our textbook. For this first chapter, the problems are on pages 21 to 25-ish and 50-ish, around there. There's actually 2 sets of problems. The easier ones are on page 21 and so forth. I'm going to be going over the even numbered problems because there are no answers for those in the back of the textbook. And this gives me an opportunity to also tell you how I like to study chemistry, or basically any science subject. First of all, I don't like to read the chapter because I don't know what's important, so I don't know what to focus on. And so I think it's a waste of time. What I usually like to do, though, is look at the pictures and read the titles and look at the headings and then get over it. It's like a comic book. Then you go to the end of the chapter problems. So this isn't an end of the chapter problem. State whether the following is a hypothesis, theory, or law of science. Global climate change is occurring because of human-generated carbon dioxide. Explain. And the explain part means, why do you think it's a hypothesis if you choose so, or why do you think it's a theory, not explain climate change. Fair enough? So here, I'm going to look for the part in the book that talks about hypothesis, theory, and law of science and how they differ. So what do we know about a hypothesis? It's basically an explanation based on, or not an explanation, it's an idea based on observations. And hypotheses are usually small things, because hypotheses must be testable. If you can't test them, it's not a hypothesis. So you can't really test with one experiment whether or not global change is occurring due to man-made or human-generated carbon dioxide. There is no one way to test that. So I would say that this idea is not a hypothesis. Also important to the hypothesis is that it must be falsifiable, or you must have a null hypothesis. What that means is that there must be some set of circumstances where if you collect the data, it will prove your idea to be wrong. And a lot of people think, well, geez, that proved my hypothesis was wrong. I just failed as a scientist. And you have not. You have succeeded. You've succeeded because you've tested your hypothesis. So failure of your hypothesis is not failure of you as a scientist. It's success. Okay? Naturally, we would all like to have a hypothesis that works. Now, what is a theory compared to a hypothesis? Well, it's a unifying body of facts, unified body of facts. No one disputes that the Earth has been warming for the last 100 years. No one disputes that. That's a fact. No one disputes that there's more CO2 being put into the atmosphere now by man than there was, 200 years ago. So those are facts. But these body of facts are unified into an explanation for why. You see how my left hand gets in the way of what I'm writing? Sorry, I'm left-handed. Luckily, I'm not Catholic because then I would be considered to be evil. But since I teach chemistry, I am kind of evil anyways. So, as a total aside, just so that you understand just how evil I am, I'm part Italian, part Japanese, and part German. So, what countries were we fighting against in World War II? In fact, they called them the Axis powers during World War II, and some people call them the axis of evil. So, at least I accept my evilness. Okay, unified into an explanation of why. Okay, and the important thing about theories are they are mutable. They will change based on the evidence. The original theory of evolution has evolved so much in the last 100 years, 150 years since it was developed. Now, what is a law? This is something that seems to be universal. For instance, when you do a chemical reaction, there's something called the law of the conservation of matter, which says that when you have a chemical reaction, whatever amount of stuff you start with by mass is the amount of stuff you end with by mass. It may or may not change into other things, but if you start with 10 pounds of material, you're going to end up with 10 pounds of material. The law of the conservation of matter. We expect that to happen regardless of whether you're doing a chemical reaction on Earth, a chemical reaction on the moon, a chemical reaction in a different galaxy. We expect that to happen. And in fact, it's because of these universal laws that we're actually able to do things like go to the moon, send vehicles to Mars, and so forth and so on. Because if the laws weren't universal, then who knows what would happen once we left Earth's atmosphere. All bets are off, and maybe you wouldn't be able to go to the moon, So this is a universal. And these are rarely mutable. They rarely change. And these are the differences. And so for these reasons that hypotheses are, pretty simple, they're testable, and this is not testable, this is a unified body of facts into an idea of why or an explanation. And this theory is changing as time goes on. It's being refined. And it doesn't seem to be a law. It doesn't seem to be universal. I would call this a theory. Are there any questions about number 2? Okay, there being none. Also, if you have a question, you can go into that reaction area and raise your hand, and I'll look for that. Okay, so here, what is the phrase meant by green chemistry? Now, this clearly means that you want to read about green chemistry. And let me show you what our book says about green chemistry. It says quite a bit. And when you're trying to think of an answer for something like this, the answer is not go find the place in the book and copy it. That's not what we're looking for here. So this is green chemistry right here. I'm going to try to zoom in on it so that you can read it better, or you can look at your own book if you have it. But many of you probably have a, what kind of a book? Ebook, which means that you would have difficulty with reading this and looking at the screen at the same time. My remote's not working. The knob on the end of this machine is finicky. Okay, that's not too bad. So let's take a look at these one by one. It is better to prevent waste than to treat or clean up waste after it is formed. If you wanted to, you could summarize this in 2 words: prevent waste. The second one, new pharmaceuticals or consumer chemicals are synthesized by a large number of chemical processes. Synthetic methods should be designed to maximize the incorporation of all materials used in the final product. Well, that means if you incorporate all the materials into the final product, there aren't any leftovers, which is what we would call waste. So this second bullet is just a more specific example of preventing waste. Next, synthetic methods should be designed to use and generate substances that possess little or no toxicity to human health or the environment. So the focus here is that we want to reduce toxicity. We don't want to make substances that are toxic. We don't want, I would assume that also this means we don't want the waste to be toxic. So reduce toxicity. Chemicals should be designed to function effectively while still reducing toxicity. I'm not sure how this adds to the whole discussion. Would you design a chemical product that doesn't function effectively? No. So it's still focusing on reducing toxicity. I think it's a given that when you're making these chemicals, you want them to work. Energy requirements should be recognized for the environmental and economic impacts and should be minimized. Synthetic methods should be conducted at ambient temperature and pressure. And the reason they say ambient temperature and pressure is because you don't have to use any energy to keep the temperature room temp. It is room temp. And you don't need to do anything to keep the pressure at atmospheric pressure. It takes energy to make it warmer or colder, and it takes energy to increase the pressure or reduce the pressure. So basically the idea here is not about temperature and pressure, it's about reducing the amount of energy required. So that seems to be another idea. You know, the first one here, prevent waste. Second one, reduce toxicity. Third one, minimize energy use or requirements. Raw materials should be renewable whenever technically and economically practical. This seems to be a new one. You want to use renewable resources so that you don't run out of materials. Chemical products should be designed so that at the end of their function, they do not persist in the environment or break down into dangerous products. Well, dangerous products sounds like the toxic part, and they do not persist in the environment means that it's kind of a waste that you don't want. So I think these are covered previously. And then you want to choose processes that minimize chemical accidents. So that's a safety issue. So I think a good summary of this one is, let me zoom out here. Oh, now my remote works. Okay, so what is meant by the phrase green chemistry. We can write in chemical processes. Reduce waste. Minimize toxicity. Conserve energy. Use renewable resources. And I believe the last one is have safe processes. So I'm just going to put safety. And that kind of summarizes green chemistry. Try to do things so that you don't have waste, you don't have toxicity, you don't use much energy, you use renewable resources, and you want to be safe about it. So does this kind of make sense for what might be considered to be a pretty good answer for this one? I'm looking for raised hands on your participant list. Or actually not raised hands, because that really means a question. I'm looking for the thumbs up. So let's see those thumbs up. Okay, I've got one. Can the rest of you find your thumbs up? Open up your participant list. So you go to the bar here, click on the participant. And when you click on the participant, at the bottom, you'll have icons. One of them should be a thumbs up. And if you don't see that icon, you go to reactions and you hit the thumbs up. Okay, if you guys aren't going to do your thumbs up, then I'm just going to open up my window here so I can see all of you. Here's the other option then. I ask you, are you with me? And you respond, "Arr, we're with you, Tony." So why don't you turn on your videos and give me a, "Arr, we're with you, Tony," or give me a thumbs up. It's your choice. Wow, those thumbs are coming up now. Maybe it's too late for me to joke with you guys, but tough luck. This is the way it's going to be. Okay, so any questions about number 4? If you do, raise your hand. Okay, then moving along. Number 8, give the name of the following elements. I want to take a moment here to tell you that you need to know the names and the symbols of about 60 different elements. And you should know them by the time of the first exam. And when I say the name and the symbol, that means if you're given the symbol Mn, you're able to write magnesium, manganese. That's a tricky one because there's Mg, which is magnesium. So you need to know about 60 elements. Which elements do you need to know? Well, if you look at a periodic table, it starts off with a hydrogen here. Over here, there's a helium. Below hydrogen, there's an Li with the number 3 above it. And next to lithium, there's a boron with the number 4 above it. And then over here, there's a Be with the number 5 in front on top, and then carbon with the number 6, and so forth and so on. So what I'm trying to show you is that when you look at the periodic table, it's arranged by the number on top, 1, 2, 3, 4, 5, 6, and so forth. It gets a little hinky towards the bottom where it kind of skips around. So I'm going to say that you should know elements 1 through 40. And what I mean by that is you don't need to know what element 1 is, but if I write the letter H, you would be able to write the letter hydrogen, or the word hydrogen. And if I were to write the word helium, you would be able to write He. That's what I mean. You don't need to know where it is on the periodic table, just the symbol if given the name if given the symbol. So you should know elements 1 through 40, plus the following elements where I'm going to give you the symbol and force you to look up the name. So beyond number 40, you should know Ag, which is silver. You should know Sn, which is tin. You should know I, which is iodine. And you should know Xe, which is xenon. You might kind of tilt your head a little when I say iodine. So I'm going to tell you why I call this iodine. This is called fluorine. This is called chlorine. This is called bromine. They all end with ene, so this must be iodine. If I want to call this iodine, then I got to call this bromine, chlorine, and fluorine. Since most of them end with ene, I'm going to call it iodine. Now, honestly, I don't care what you call it, as long as you call it iodine or iodine. Okay, there are more. You should know cesium, barium, lanthanum. You should know PT, which is platinum, Au, which is gold, Hg, which is mercury. I'm going to move this piece of paper up. You should know Pb, which is lead, Po, which is polonium, Rn, which is radon. It's that gas you hear about that creeps up in your basement and is radioactive and toxic. You should know francium, radium. These two are often confused. Radon has an N in it. Radium does not. The few others that you should know are, you should know U, which is uranium. You should know Pu, which is plutonium. And you should know Am, which is americium. So these are the elements I want you to know. These 40 plus however many these are. And then, of course, there is this element here, which is, you know how there's state birds and county birds and so forth and so on? This is Humboldt County's element. Erbium. You guys are so dead. That's funny. Erbium. Humboldt County's. Okay. I'm going to keep going. Clearly, it's too late for you guys. I want you to take a nap before you call in tomorrow. That way you're fresh. Or do what I do, just drink a lot of coffee. Okay. There's another thing I want to tell you about the symbol of elements, and that is when you have two letters, the first one is always uppercase, and the second one is always lowercase. So when I wrote helium, this is correct. This is not correct because that E is an uppercase. Uppercase and lowercase do not refer to how tall it is. They refer to the look of it. There are some letters where the uppercase looks like the lowercase, like O's, right? U's, the uppercase looks like the lowercase, P's. But a lot of the letters, the uppercase and the lowercase look quite different, like an A or a B or a D or an E. So it's always uppercase, lowercase, and something like this is considered to be wrong. Is there anything unclear about that? If so, let me know. Okay, moving along. Let's take a look at this question. See what you can do on your own. and then I'll answer the questions. I'll give you just a minute here. I just ripped a piece of paper. You might be wondering, why don't I just write the answer next to this? And the reason is that I hope to use this same piece of paper next semester. So I don't have to write the thing out again. So silver is Ag. Aluminum is Al. Now, a lot of people don't like that, but since I make my eyes look like this for iodine, when you see that, that's an L. If you don't like that, don't do that, because that looks like an uppercase L. Do one of these things here where you kind of bend the end of it. Whoops, I just wrote all. Bend the end of it like that. Is that clear? All right, plutonium, Pu. Tin is actually Sn. And just for the same reason that silver has a symbol different than its name, there's no A in silver and there's no G in silver. It's because the Greek name for silver starts with an Ag. For tin, the Greek name for tin is stannous or stannic. So that's why we get the Sn. Technetium is Tc. And krypton is K lowercase r. Okay, so let's go ahead and move on from that. And let's look at this problem number 12. In each of the following pairs, decide which is an element and which is a compound. And you'll notice that in this first problem, they give us a formula and they give us two formulas. In the second one, they give us two names. And in the third one, they give us two names. So we need to make the decision based on the name and based on the formula. So it's really simple when you're given formulas. For this one here, if the formula given is only one type of element, then you say it's an element. So these are found on the periodic table. If you take a look at the first part of A, there's more than one element here. There's platinum, there's nitrogen, there's hydrogen, and there's chlorine. When you see all of these elements squished together like that, that means it's a compound. So element, compound. I went a little further earlier today and explained what all of this means with the parentheses and all. If you get rid of that parentheses, it means that you have two NH3s. So here we have PT, NH3, NH3. And this little 2 means that you have two chlorines. Well, this 3 means you have three hydrogens and three hydrogens. Chemists decided a long time ago that they don't want to do this. It takes too much effort. And so this is a shorthand way of writing this, but also this gives you structure for the compound. So we know how things are connected together. So this is important to learn, and we'll be learning that as the semester proceeds. Now, for letter B, how do we make the decision? And the answer is if the name has only one element in it, it's an element. But if the name has more than one element in it, even if it doesn't say oxygen, but it has an additional layer to it, it's a compound. So here, this is an element and this is a compound. Now, based on this question, we know that one is an element and one is a compound. So based on these two words, silicon does appear on the periodic table. This is the element. Turns out that sand is actually a compound, but we have a common name for it, sand. Any questions here about how you would decide between a compound and an element? Element, one type of symbol, compound, two or more. So here's a question for you. We all know that we breathe oxygen, correct? That's the formula for oxygen, element or compound. So Here's where you get to vote. If you go to your reactions, you can see a go faster and a go slower. So this is go faster, this is go slower. I want you to pick go slower if you think it's an element, and I want you to pick go faster if you think it's a compound. And there's no shame in getting it wrong. You're just trying. Element or compound? Wow, this is like watching the Dow Jones. It's just going all over the place. Okay, for real, it's what I imagine looking at the Dow Jones would look like, because I don't watch the Dow Jones. So no one's voting. What are you guys afraid of each other? I don't see oh, is there a tally? Oh, I've got one of each vote, which means 3 of you aren't voting. And the answer is it is an element, because there's only one type of symbol here. Okay. Turns out that there are 7 elements that when you buy a jar of it, the atoms come in pairs, like Noah's Ark, right? They come in pairs. All the rest of the elements, if you buy a jar of it, the atoms are not stuck together chemically. They're just stuck together because they're next to each other. Okay. So those 7 elements are the following. Hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. And you can make this into like syllables: Han, Col, Brif. And that's one way to remember it. Another way to remember it is this way. Have no fear of ice cold beer. Have, hydrogen, no, nitrogen, F, fear, fluorine, of, oxygen, ice, iodine, cold, chlorine, beer, bromine. This one I don't like so well because the first 2 letters of cold actually are cobalt, and the first 2 letters of beer are beryllium. So this might fail you. So you could say have no fear of ice-clad bratwurst, because that way you have a CL and a BR. And the reason you should not be afraid of ice-clad bratwurst is because you can grill them, and most people think they're wonderful. So give me the thumbs up if you like bratwurst. Oh, I've got I don't eat bratwurst myself. Not into them. Okay, moving along. A sample of the compound magnesium oxide is synthesized as follows. 60 grams of magnesium is burned and produces 100 grams of magnesium oxide, indicating that the magnesium combined with 40 grams of oxygen in the air. We could actually write out this reaction. It says 60 grams of magnesium. We know the symbol for magnesium is this. Reacts with 40 grams of oxygen. We know oxygen is a Hunkelbrief, and it makes magnesium oxide. We don't know the formula of magnesium oxide yet, unless you've taken a previous chemistry class and you remember how to figure it out. You start off with 60 grams of this and 40 grams of this, and you get 100 grams. So what do we notice about the before and after by mass? You should notice that you start off with 100 grams total, of material, and you end up with 100 grams total. I mentioned this law earlier where the amount of stuff you start with is the amount of stuff you are left with. So in this example, if we actually started with 50 grams of oxygen, we would end up with 100 grams of magnesium oxide plus 10 leftover grams of oxygen that are unused, because these things have to mix in particular proportions. Okay, so these are the proportions in which they mix, 60 of this with 40 of that, and you get 100. And you don't have any leftover unused material. This sounds like green chemistry, doesn't it? Also, magnesium oxide is not toxic. You could actually use it as sunscreen. Okay, so now they ask if 30 grams of magnesium had been used, what mass of oxygen would have combined with it? So the question is, if we have 30 grams here, how many grams of oxygen would we have needed? And the answer is pretty straightforward. If we're using half of the magnesium, we should need half of the oxygen. So our answer, 20 grams. Now let's do one more step. How many grams of product would we expect? And if you said to yourself, 50 grams, you are correct. Any questions there? So what law of chemistry is used in solving this problem? The law of the conservation of matter.
I have one question.
Sure, go ahead.
Where, like, so in this magnesium takes half as much oxygen. Where do we look to like find the conversion or whatever? Like how
Well,
much? What?
You don't need the conversion. You can actually just think it through. If you're using half the magnesium, you would expect to use half the oxygen.
Well, yeah, but let's say if they were both different elements, like to make a different thing.
Well, in this particular problem, they give you those amounts so that you don't have to figure that out right now.
Oh, okay, okay.
So they're assuming that you don't know much, so they're giving you everything. So we could do this experiment though. For instance, we could take a strip of magnesium and we could weigh it. And we could react it with oxygen in the air. And then we could weigh the product because it happens to be a solid. Now it's very difficult to weigh oxygen because it's a gas. So let's say we started with 15 grams of magnesium and we ended up with 25 grams of product. Can we figure out how much oxygen had to react with the magnesium to make this? And the answer is absolutely.
Yeah.
If you get 25 grams of product and you started with 15 grams of magnesium, there's 10 grams that's not accounted for. So we must have used 10 grams of oxygen. Okay, so they could have actually said, we start off with 60, we get 100 grams, how much oxygen was used? And that's kind of the way we do that stuff experimentally when we can't weigh things. In fact, we're going to do this lab this semester. And when I say we're going to do this lab, this is a lab that generates a lot of energy. So it's dangerous. If you've ever seen a magnesium flare burning, that's this lab. But we're not going to do that because it's too dangerous for you to do at home. So I do it as a video and you watch it, and I put things on the balance so that you can write the numbers down and so forth and so on and work it out. So does that help with your question, Henley? Was that Henley?
Yes, that helped a lot.
Okay, good. Now, I just got lucky and guessed what you were kind of meaning there about where do you get the numbers from. So if I interpret your question incorrectly, you got to let me know. Capiche?
Gotcha.
That goes for all of you. There are actually maybe 6 of us here now that I think about it.
Quick question.
Yes.
So going off of what Henley was saying, we're basically making an assumption that the ratio is going to be the same, right?
Well, there is something called the law of constant proportions.
Right.
The law
Okay.
of constant proportions says that by mass, the proportion of each element will be the same in a compound.
Right. Okay. Yeah.
So when you have a 60-40 split, it's always going to be that proportion. And since you asked, Izzy, let me show you something that we'll be doing in a later part of the chapter and actually in further chapters. So based on this reaction, we could say that 60 grams of magnesium equals 40 grams of oxygen equals 100 grams of magnesium oxide. Now, when you first look at this, you think that's ridiculous. Magnesium and oxygen aren't the same. They can't be equal. But what this is it's like saying 20 slices of bread equals 10 sandwiches. Now, I'm not trying to say that you only need 20 slices of bread to get 10 sandwiches. You need the filling, absolutely. But what I'm saying is 20 slices of bread will get me 10 sandwiches. So that's what this equal sign means. Now, when you have an equal sign, like 12 inches is equal to 1 foot, watch what happens when I divide each side by 12 inches. Because that's one of the rules in algebra. If you divide one side by a number, you got to divide by the other side by the same number, so it's still equal. So we get 1 is equal to 1 foot over 12 inches. If I take my 12 inches equals 1 foot, and instead I divide by 1 foot, I get 12 inches over 1 foot is equal to 1. So here, when I have an equality, I can take either side and put it on top, and the other side put it on the bottom, and I get a value equal to 1. And there's something in math called the identity law. So universal. If you multiply something by 1, you don't change the amount. So here, if we were to take 24 inches and multiply by this right here, 1 foot over 12 inches, the inches cancel. 24 divided by 12 is 2, and we get 2 feet. So this says that 24 inches is equal to 2 feet. Have we changed the amount? Well, if this is 2 feet, it's also 24 inches. I have not changed the amount. Are you guys with me there? So how does it apply to this? And let me show you by pulling this down. So we have the 60 grams of magnesium and the 40 grams of oxygen. If we start with 30 grams of magnesium, we would multiply by one of these two on the bottom and one on the top. I'm going to put the 60 grams of magnesium on the bottom so that the grams of magnesium cancel. And I'm going to put the 40 grams of oxygen on top. And when we multiply these together, we get 20 grams of oxygen. And this says that if we started with 30 grams of magnesium, we would need 20 grams of oxygen. So this is something that some books call the conversion factor method. Some people call it dimensional analysis. Some people call it unit analysis. It doesn't matter what you call it. It's basically using the units and the labels to help decide what goes on top and what goes on the bottom, like here. And also we're taking a particular amount and we're not changing the amount. We're just getting a equivalent amount. And in this case, it's an equivalent amount of another chemical that reacts with the magnesium. Okay. So I think we're ready to move on to 22. I don't know, did I answer your question there, Izzy? Okay. Number 16. In each case, decide if the change is chemical, is a chemical change or a physical change. So what I'd like to do here is write out what the hallmark is, the definitive difference between a chemical change and a physical change. So chemical change is a change in formula. So if we had, for instance, O2 turn into O3, this is a chemical change. This is oxygen that we breathe turning into ozone. This is a chemical change because the formulas are different. The formulas are different because the number of oxygens in the compound are different. Now, if you had H2O, S, that's solid, turn into H2O, which is liquid, this is basically ice turning into water. This is a physical change. And in this physical change, we call it a change of state. So how do I know based on this that it's physical? And the answer is the formula H2O has not changed. It is still H2O. Okay, so that's the hallmark. But what if you are given a problem where you don't see formulas? What do you look for? But before I go into that, let me back up and say that there are times where you have two things combined together. So this is hydrogen gas and oxygen gas, and you can make H2O, liquid. So based on what I just told you, is this a chemical change or a physical change? Take a moment, answer it, give an explanation, and then I'll tell you if you're right. Okay, the answer is it's a chemical change. Because H2 is not the same as H2O, and O2 is not the same as H2O. Formula has changed. This is a chemical change. Has there been a physical change here? And the answer is absolutely. Gases have turned into a liquid. There's a physical change. Most chemical changes also have physical changes. So when you're asked the question, is it a chemical change or a physical change? You're basically being asked, did the formula change? Okay, that's the real question. Because most chemical changes come along with physical changes, or they have physical changes with them. So I'm going to go back to what I was talking about before, which is, well, what if you don't have the formulas? How can you tell? Chemical changes are hard to do and undo, or I should say, or undo. Hard to do or undo. There's another one I wanted to give you for kind of what you might look for. I don't remember what it is, but it'll probably pop into my head. So with these in mind, let's take a look here at these different things. A cup of household bleach changes the color of your favorite t-shirt from purple to pink. We don't have any formulas here. So is this a chemical change or a physical change? So if we can't answer it based on formula, we answer it based on, is it hard to do or undo? Well, clearly it's not hard to do. You just throw bleach in there and it turns pink. How easy is it to turn the pink back to purple? And I'm not talking about putting your t-shirt in the washing machine and adding purple. That's not undoing, that's covering. How easy is it to turn the pink back to purple? If it were easy, they'd sell the product on TV. The ShamWow guy would be saying, oh my goodness, we got this stuff that'll reduce the effects of bleach. We call it unbleach. And you'd be buying the product by the, bucket load. Because who hasn't ruined a piece of clothing by bleach? Hard to undo. Therefore, A is going to be chemical. Any questions about A? B, water vapor in your exhaled breath condenses in the air on a cold day. So when they say water vapor, what's the formula of the water? You all know this, H2O. When it condenses into a droplet, what's the formula of the droplet? H2O. So here the formula has not changed. So, and it's actually easy to undo. If you get condensation like that, I can get rid of it pretty easily just by waving my glasses around and it's gone. Okay, so pretty easy to undo. B is a physical change. Plants use carbon dioxide from the air to make sugar. Okay, let's take a look at this. Carbon dioxide, element or compound? And the answer is compound, because we know carbon is on the periodic table. There's a second part to the name which tells us this is combined with something else. And if you're guessing it's combined with oxygen, you're absolutely right. Compound. From the air to make sugar. Do we think sugar is a compound or an element? Well, let's take a look at our periodic table and see if any one of those boxes says sugar at the bottom. Because if it does, sugar is an element. So why don't you go ahead and take a moment and look for sugar on the periodic table. Izzy says, no, I'm not going to do it because it's not there. The closest thing we have is S, which is sulfur. So sugar is not an element, which makes it what? A compound. Now, these compounds have different names. Why do you think that is? And the answer is simple, because they have different formulas. So CO2 turns into sugar. This is a chemical change. If we actually look at the formulas, it looks like this. CO2 reacts with oxygen, and you get C6H12O6. This is the formula for glucose. It's also the formula for fructose. And they also call these things carbohydrates. Sugars are called carbohydrates. Take a look at this formula. So this is the same formula as above. This is carbon with water. Water is called a hydrate. What do you do after you exercise? You rehydrate, right? With H2O. Carbon hydrate, carbohydrate. So maybe you didn't know that before, maybe you did, but that's why they're called carbohydrates. Basically, the amount of carbon is equal to the amount of water, same ratio. In glucose and fructose, it's 6:6. There are other carbohydrates where it's 1:1, 2:2, 3:3, 4:4, all the way up to 7:7. Okay, how about this next one? Butter melts when placed in the sun. Depending on how long-winded you are here, you could answer this two ways. First, you could say, well, it's simply a physical change because when you take out of the sun, it resolidifies. Or you could say it's a chemical change. And the reason you might say it's a chemical change is because, well, when you take it out of the sun and you taste it, it doesn't taste the same. And that does happen if you leave it out in the sun for a long period of time. But the reason that happens is because it reacts with oxygen and it becomes rancid, spoiled. So if it were the same compound before and after, it should have the same taste before and after. But if it tastes different, that means you had a chemical reaction. So has anyone ever had rancid butter by accident? No? It's nasty. You don't want it. It's kind of bitter. Okay, any questions on number 16? Then we shall move on. Which part of the description of a compound or element refers to its physical properties and which to its chemical properties? So let's take a look at A. I'm going to make a little list here that says chemical, and over here, physical. Calcium carbonate. That's a chemical property because it's a formula. And if you change the formula, that's a chemical change. White, that's a physical property. Solid, physical property. And now I remember another way that you look at physical properties versus chemical properties is you ask yourself, is it something you could determine without changing it into something else? Can you determine that calcium carbonate is white without turning it into something else? Yeah, you just look at it. Split the pile in two, they still both look white. Solid is the same thing. Now, there are some limits about the changing it into something else, because sometimes when you change it into something else, you're really just changing the state. So when ice turns into water, you're just changing the state. You're not changing it into something else. Okay, moving along here. Density. The density is a physical property. It's something that doesn't change based on the amount you have. Density is one of those things that you use to determine if something is going to float in water or sink in water. If the object has a density greater than water, it will sink. It has a density less than water, it will float. A twig floats on water because it's less dense. A tree made from the same material as a twig also floats on water because it's less dense. A pebble sinks because it's more dense than water. A boulder sinks because it's more dense than water. Okay, let's see. Reacts with. Reacts with. To produce. That is a chemical change. These are key words for reactions. React and produce. And in fact, if we go back to this example here, the reactants are on the left side and the products are on the right side. So these guys react to become these products. Let's see now. Gaseous, that's a state, so that's a physical description. And carbon dioxide, again, is a chemical property because it's telling us about the formula. So any questions about A? So let's take a look at B. So what about the word gray? Chemical or physical? Physical. How about powdered? Physical. How about zinc? That's a formula. It's a very simple formula, Zn, but it is a formula. Metal. I would argue that metal can be considered to be a chemical property or a physical property. And we'll learn more about that later. Purple. Definitely a physical property. How about iodine? And here, notice I'm going to put I2 because iodine is a honkelbrief. It's the I in brief. To give a white and then compound. Are there any questions here? Okay, let's move on. A solar panel is pictured. So you all know what a solar panel looks like. I'm not going to bother showing you the image in the book. When light shines on the panel, it generates an electrical current that can be used to recharge the batteries in an electric car. What types of energy are involved in this setup? So here, the two types of energy that we normally talk about are kinetic energy, which is the energy of motion, and potential energy, which is stored energy. I'm going to give you 4 examples of kinetic energy. One example is translation. So in the physical world, translation means moving from one place to another. So a ball being thrown to a catcher, that's translation. A river flowing downstream, that's translation. They're both examples of the same type of kinetic energy. Me moving my mouth, translation. There's sound. So sound is different than translation because air is not actually moving from one place to another. It's pulsing. It's pulsing. I want you to imagine a jump rope where you hold it between 2 people and one person takes that rope and they whip it to the other person. A little hill of energy moves to the other person. And when they're done, the rope hasn't moved, but energy has moved along the rope in that little hill of energy. And you know there's energy there because if you put your face in front of it, you're going to get slapped. So the rope doesn't actually translate, but energy moves along it, just like sound moves. So when I speak, the air is pulsing, and that's what you're interpreting as sound, me pulsing the air. If I was actually moving air away from me, because of the amount of that I talk, I should have suffocated by now because I've moved all the air away from me, but that doesn't happen. I know you're thinking, darn it. Okay. Another type of kinetic energy is going to be heat. So heat, in chemistry, we usually think of that as starting with atoms vibrating. So they vibrate. And then they vibrate enough so that they start moving relative to one another, but they're still close together. That's a liquid. And then finally, they get enough energy where they fly apart, and now they're a gas. So heat, that vibration, and that change from vibrating to moving, translating, and then to moving with even more translation is considered to be kinetic energy. And you can turn one type of kinetic energy into another. The last type of kinetic energy is electric current. And the way electric current is that the electrons are actually moving from one place to another. So you might think, well, this is just translation, but it's a special type of translation. When you have electric current, it's like a game of musical chairs. Only in musical chairs, there's always one less chair than there are persons. So someone's left standing, and then you continue with the game by taking out another chair. For electric current, there's always enough chairs for all of the electrons. So when the electrons move, another one fills its spot. So it appears as if nothing is ever changing, yet the electrons are moving. So this is considered to be a 4th type of kinetic energy. Now, the types of potential energy. For electrical current, there's something called electrostatic. Electrostatic is when you have charge buildup, and we all know what this is like in a dry climate when you reach for a car. You get too close and that electrostatic energy turns into electric current and you get zapped. And so that's an example of potential energy being turned into kinetic energy. We also have position due to gravity. So if I were to hold my cup above my head, there's a certain amount of kinetic energy in my mug. And if I raise that mug even higher above my head, there's even more energy in it. It's got potential. And when you take that mug and you hold it up and then you raise it, this is now kinetic energy. And when I stop it, it now has more potential energy. So you can turn kinetic into potential and potential into kinetic. So position due to gravity. There's also the spring. And when we talk about the spring, it could be either compressed or it could be stretched. They're both the same type of example. So a compressed spring would be like when you jump on a pogo stick and it compresses. When you get to the bottom of that compression, there's potential energy and immediately it shoves you back up into the air. Stretched would be like a rubber band. When you stretch out a rubber band and hold it, it's got potential. And then there's one more type of potential, and it's chemical potential. And this is due to the bonds in a compound. So for instance, there's something called TNT, which is an explosive. It has chemical potential. There's something called dynamite, which is explosive also. It has chemical potential. There's something that you may have heard about in a biology class called ATP, adenosine triphosphate. It's called the energy molecule of biology because it has chemical potential and it's stored energy. So when we apply this to this particular problem and we think about what's going on, we're going to look at electric currents. So that's kinetic energy because electrons are flowing. You recharge the batteries. Batteries store energy. And this seems like it's a chemical potential, and it is. But then there's also light. So I did a little reading today. Is light energy? And I read this one guy who said, light is not energy because it does not have mass, which is the stupidest thing in the world I've ever heard. Can light melt butter? What do you think? Can the sun melt butter? You bet your bippy. Does it take energy to melt butter? You bet your bippy. So is light energy? You bet your bippy. Now, is it something that we can store? Can you walk around with a box of light? No. Light moves from one place to another, so it's kinetic energy. I'm not sure where you'd fit it into all of this, but I'd call it translation as the purest form of energy. It's moving from one place to another, just as pure energy, not in a box, not in anything, not combined with any chemical compounds. It's pretty fantastic. So, I almost feel like putting light here as another type of kinetic, but our book doesn't do that. Okay, so does everyone understand that we're looking for this particular problem? Kinetic energy that is used to make more kinetic energy that is eventually used to be stored in batteries as potential energy so that you can use it during the night. Capiche? Okay. I don't know. We've been going for an hour and 10. Since this is related to the previous problem, let's go ahead and do this one and then we'll call it quits. Sound good? Okay. That was a pretty quick thumb up there, Izzy. Izzy says, I want out. Determine whether kinetic energy is being converted to potential energy or vice versa in the following processes. Water cascades downward in a waterfall. So water cascading, potential or kinetic? I'd say it's kinetic because it's moving, wouldn't you? Downward in a waterfall, that's still kinetic. I don't know how these are different. But let's change this a little bit. The water in a dam is released? Water in the dam, kinetic or potential? Potential because it's stored in a dam. The water being released and moving downhill, kinetic or potential? Kinetic because it's moving downhill. Now, if we wanted to ask specifically, what type of potential is this? Well, since it's stored at a higher level than where it ends up, it's potential due to position and gravity. The water cascading down, is that kinetic? Well, we said it's kinetic. Is it electrical current? Is it translation? Is it sound? Or is it heat? And naturally, we're going to say that's translation. Although some people could say, well, I've been near some waterfalls where it's so loud that there's a lot of energy there. Absolutely. But I think the water just dropping would be called translation. How about a player kicks a football? Kinetic or potential? See, this is another one. A player kicks a football. To kick a football, you got to move your leg, right? And here, if we think of the football in flight, it's also kinetic energy. But I think what they mean here is that the player's kicking and the football is stationary. So the football really just has potential energy. But once it's kicked, it's turned into kinetic energy. So here we could say this is the kinetic energy that we start with. This is the potential. Once they meet together, you're turning that football into kinetic. Okay. So this question here is deceivingly simple considering what we're looking at here. Okay, electric current is generated by a chemical reaction in a battery. Well, the battery is definitely stored energy. So the stored energy is being turned into kinetic energy because it's an electric current. This is kind of written backwards, saying this is what happens because of this. So I'm going to say this one is a lot easier than the rest. Here we have stored energy being turned into kinetic energy. And I would actually say this is chemical potential being turned into electric current, which is kinetic. And lastly, water boils when heated on a stove. There's so much we could say about this. Heat, kinetic or potential? Kinetic. Okay. Boils. Well, if it is boiling, kinetic, because you see bubbles rising through it. Does the water also, though, hold potential energy in it at all? And my answer is, I don't really think so.
Give me a second. My game is taking a million.
To me, all of this is pretty much chemical.
Okay, I'm gonna grab. I
Excuse me, not
totally
chemical.
forgot about this, and you probably did too. You know the contraption to get.
There we go. I have the power to mute. So all of this looks like kinetic energy to me. The water boiling, heat. I'm not sure where potential is. So I would say this is a kinetic energy being turned into another type of kinetic energy. Capiche?
For number D,
Did you say number D?
I mean, yeah, I think I'm just yeah, letter D. For letter D, so the stove isn't like potential energy, like the fact that you're using like a gas stove or something, that's not potential.
Well, actually, if we know how stoves work, stoves don't store gas.
That's true.
So, but I understand what you're thinking
Oh,
about.
okay.
Well,
Never mind. Yeah, I get it.
I do understand what you're talking about. You're thinking about, well, what about the gas?
Right.
The gas is potential energy. It's stored chemical energy. So if you add gas to this equation, you could say the gas is definitely stored energy. The potential lies in the chemical bonds of the gas. And when it reaches the burner, it turns into kinetic energy. And that kinetic energy is used to boil the water. So definitely you can look at it that way. And I'm glad you brought that up, because maybe this is what the person had intended. But, you know, if they had intended this, I would have said something about a gas canister is used to make a flame. Because then it's easy. You say, well, gas canister stored, flame, kinetic.
Mhm.
These are too tricky, I think, considering what we do know.
Mhm.
But that's a good observation, Izzy. All right. Okay. All right. So at the end of every session, you're supposed to turn on your mics and say goodbye to everybody.
Bye.
Goodbye, everyone. Goodbye. Everyone's so quiet. All right. I will post this recording in your module. Arg. Ah, that was the pirate time.